This video is about a very important rule called the factor theorem. We'll get to that in just 1 second. You are looking at a polynomial graph. I know it doesn't really look like a polynomial, x minus a times x minus b times x minus c, because it's all factored out. But if I were to FOIL that back, I would get some cubic polynomial, x cubed with a whole lot of junk afterwards. And from what we saw from earlier in this lesson when we talked about end behavior, the end behavior of this matches the end behavior of a cubic function. As x approaches infinity, f of x approaches infinity. And down here, as x approaches negative infinity, f of x approaches negative infinity. What I want to focus on now is not the end behavior, but really what's happening in the middle. So what I want you to notice, and this is something that we saw when we did quadratics also, the factors of your polynomial directly connect to the x-intercepts of the polynomial as well. Notice how this a is a negative 2, so this factor is x minus negative 2. If we were to see it written out, it would say x plus 2. And this factor translates to a root, or an x-intercept, of negative 2. So if I were to move that root, maybe make that a be negative 3, well, now the x-intercept has moved to negative 3. Notice how the other ones didn't move. Of course, all the other points on the graph did change. Got steeper and bigger and farther apart. But the x-intercepts of 1 and 4 didn't go anywhere because those are the factors x minus 1 and x minus 4. Of course, the factor of x plus 5 means the x-intercept here is 5. If I move that back to 2, to negative 2, we're back to where we started. I can move this b, I can control this b, maybe move the factor up to 2, to 3. See how the x-intercepts are following along with it. If I move this down to negative 1, notice how now there's an x-intercept at negative 1. So these always work out this way, that the factors and the x-intercepts are connected to each other. There's a name for this. It is called the factor theorem. If x minus a is a factor of f of x, then a, whatever that number is in here, is a root of f of x. And it works vice versa. It works the other direction too. So if a is a root, then then x minus a is a factor of f of x. And just a quick note, when we say a is a root, that means, another way of saying that means f of a equals 0. That's something to keep in mind. So all I'm saying is that a factor and a root go together, always and forever, no matter what. We saw this when we were solving our quadratics by factoring also. Whenever we factored, we could split and solve using the zero product property. The factor eventually became a root. The reason why this is so important to us now in this unit is because, unlike the unit on quadratics, we are often going to be faced with cubics that we just can't factor by looking at them. X cubed plus 6x squared minus x minus 30. I can't factor that just by looking at it. So what we're going to do instead is, number one, we could look at the graph of x cubed plus 6x squared minus x minus 30. If I turn that off for a second, and I'll graph x cubed plus 6x squared minus x minus 30, I can see there is a x-intercept at 3, which means that x plus 3 is a factor. That's one thing you can do. Of course, that doesn't always work for us because you can't always use a grapher. So we need another way to show that x plus 3 is a factor of x cubed plus 6x squared minus x minus 30. What we're going to do is rely on the factor theorem to show that if x plus 3 really is a factor of f of x, then a must be a root, which means, another way to say this, is that x minus a must go in evenly to x cubed plus 6x squared minus x minus 30, which means if we do the synthetic division, we should get a remainder of 0. That's how you know that a factor goes into a polynomial. If when you try and divide the polynomial by that factor, so I'm going to divide x cubed plus 6x squared minus x minus 30. I'm going to divide that by x plus 3, or x minus negative 3. I should get a remainder of 0. That's what I'm looking for. Let's do the synthetic division. Bring down the 1. Bring down the 1. Negative 3 times 1 is negative 3. Combine. Negative 3 times negative 3 is negative 9. Combine. And negative 3 times negative 10 is 30. And when we combine those together, we get 0. That was a little bit bigger. It would have been more dramatic. There we go. That's our 0. That's great. That means that x plus 3 really is a factor of x cubed plus 6x squared minus x minus 30. And the quotient, when we divide x cubed plus 6x squared minus x minus 30, if we divide it by the x plus 3, what we're left with is this, x squared plus 3x minus 10, which we can factor because now it's a quadratic. Now we know how to deal with it. And that's going to be the theme of this unit. Now it's a quadratic. Now we know what to do. This factors to x plus 3 times x minus 2, which are our other two factors of the original cubic, which we can see by looking at the original cubic. It also has x-intercepts at negative 5 and 2, which means that its other factors are x plus 5 times x minus 2. If we didn't have that grapher to look at, we still could have done a pretty good job of graphing, or at least sketching a graph, knowing what we know now, that since x plus 3 is a factor, let me just prove that. That means that negative 3 is a root. And we also found that x plus 5 is a factor, so negative 5 is a root. X minus 2 is a factor, so 2 is a root. And we also know end behavior, because it is a cubic function. We know that as the function, or as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches negative infinity. So we know that our end behavior is going to be going up there and down there. And slightly sneakier one, something else we can say, is that there is a y-intercept we can identify also. Because if I look at the original function, or the original polynomial that we were looking at, if I try and plug a 0 in, that'll be 0 plus 0 minus 30. So finding the y-intercept of a polynomial is always super easy. If it's in polynomial form, it's just the constant at the end. So I'm going to have to, I'll count by 6's here. Negative 6, negative 12, negative 18, negative 24, negative 30. And so now I can connect my dots. I don't know exactly how high up it goes, but I know it needs to turn around. I know it needs to turn around again. And there's a sketch of my graph. You can see how it compares to the actual thing. Not too bad. I was a little bit off at this turning point down here. What are you going to do? The extension of the factor theorem is that it goes the other way too. We just took a polynomial and used one factor to find the others. Well, we can go the other direction too. If we're given the factors of a polynomial, or the x-intercepts of a polynomial, I should say, we can turn it into factors, and then if we wanted to, we could FOIL it out to write the polynomial. So any function that has roots at -3, 2, and 1 must have factors at x plus 3 times x minus 2 times x minus 1. The next question on here, write a second function with the same roots. Well, that's a little bit sneaky, except it's incredibly easy to answer because any other function that has these three factors will have roots in the same place. What I could do to make it a different function is just stick a coefficient on here. Any number I want, 2, -1, 55, doesn't matter, I could stick that on there. So here is that same function. It's FOILed out in this case. Actually, this appears to be a different function, but you get the idea. Let me shrink down my window so it can actually fit on your screen. So here is a times some function. This does factor to x plus 1 times x minus 1 times x minus 2. Apologize, I forgot this was a different function. But there's an a, and watch what happens as I change the a. Look at those three x-intercepts. They go nowhere. Even as everything else in the function changes. My a is much bigger, so now my function is steeper. Or I can make my a be negative, which would flip the whole thing upside down, and my end behavior is totally opposite. But no matter what I'm doing, those three x-intercepts are not changing whatsoever. The y-intercept is changing, which means I can use the y-intercept to find a. So we'll look at one other example here. We'll jump to this next one. We'll jump to the second one here. Skip over that and go here. So make it a little bit bigger so you can see. I want to write the equation of this. And this is the one that matches the x-intercepts I just showed you before. So we can say, just by looking at the x-intercepts at -1, 1, and 2, that this function is something, I don't know what, but because I don't know what that lead coefficient is, I need to fill it in with some name, so I'm going to call it a, times x plus 1, times x minus 1, times x minus 2, from the three factors from those three x-intercepts. The other thing I do know for sure by looking is that f of 0 equals -4. So all I have to say is that f of 0 is equal to -4. But f of 0 is also the same thing as taking a 0 and plugging it in for x. 0 all of those out. So that would be a times 0 plus 1 times 0 minus 1 times 0 minus 2. If you want to, you can FOIL out that polynomial and plug in a 0 then, but you don't have to. And so my equation, I've got -4 has to be equal to 1 times -1 times -2 is just 2. Hey, well, I can solve that. So my a is -2, so my function that is graphed there is -2 times x plus 1 times x minus 1 times x minus 2. And now our end behavior from that negative sign matches what I see, and the y-intercept matches as well. If you're told to FOIL, if you're told write a function in polynomial form or write a polynomial, then you would have to do the FOILing. But if you're not told to, don't. leave your answer factored, and that's totally fine too.